All right, welcome to section 8.5, writing and graphing exponential growth functions. So we've been dealing with exponents. That's where the exponential part comes from. And growth means that something's getting bigger, it's growing. 8.6 is actually decay. So we're first going to master growth, and then we'll worry about decay. So we have some vocab here. First of all, what is an exponential function? It's a function in the form of y equals ab to the power of x. A cannot be 0, B has to be bigger than 0, and it can't be 1. So it could be a half, it could be 4, but it can't be 1, and it can't be a negative. It can't be less than 0. Exponential growth is a quantity that increases by the same percent over equal time periods. A quantity that increases by the same percent over equal time periods. And compound interest is interest earned on both an initial investment and on a previously earned interest. So you earn some money, you just reinvest it, and now you earn more interest on that initial investment plus the interest you had previously earned. All right, so down here for example 1, they want us to write a rule for the function. The first thing we need to do is we need to make this number 18 because there's a little typo there. That should be 18, not 8. And the second thing is you're going to make this table over here on the left because I want to review how to write a linear function before we worry about writing exponential functions. So refresh your memory. What is the general form of a linear equation? I hope you said it's y equals mx plus b. You could have also said standard form or point slope form, but y equals mx plus b is kind of the one we use all the time. So m stands for what? It's the slope, right? Which is the rise over the run, or the delta y over the delta x, the change in y over the change in x. So what you need to do is find your change in the y values. And what you notice in this problem, they're all going up by 3. So my delta y is 3. My delta x is going up by 1 each time. So the slope of this problem is 3. So it's y equals 3x plus, and then I need my b. B stands for what? The y-intercept, and I have it in disguise right here at 0, 1. There's my y-intercept, my b, and so I just need to write plus 1. If you didn't notice it was in disguise, you may have already started by plugging in a value for y and for x and solving for b. You would have still gotten 1 that way. Okay, so that's a quick little review of writing linear equations. We've done that previously this year. Now we're going to worry about writing exponential equations, exponential function rules. Okay, so the first thing we need to do is we need to tell whether it is exponential. And here's the deal. If the y values multiply by some number and the x values increase by 1, which they do, we have an exponential function. So let's see. What can I multiply each value by to get to the next one? It's 3, or 3 over 1 in the case of the fractions. So we are multiplying each one by something in the y's, and the x's are going up by 1. All right, so first of all, kind of filling in here, it says tell whether the function is exponential. Here the y values are multiplied by 3 for each increase of 1 in x. So the table represents an exponential function in the form of y equals a b to the x, where b equals 3. So there's the deal. This magic number that they're getting multiplied by is b. It does not stand for y-intercept in exponential functions. I know it would have been nice if they would have made it like that, but it doesn't. B is whatever number it's being multiplied by. The next thing we have to do is we have to find the value of a. To find the value of a, we're going to find it when x is 0. So in my exponential equation, y equals ab to the x, if I put a 1 here for x, this is what happens. And what do we know about any number to the power of 1? It's 1, right? So now I have a times 1. Well, anything times 1 is just itself, a. So when x is 0, I know what a is. When x is 0, I know what a is. When x is 0, I know what a is. What's a? 2. So A is actually the y-intercept now. Boy, it would have been nice if it was the B, huh? It's not. So A is 2. And now we're going to plug those both in to write our equation. So we have y equals 2, because it's a, b to the x, so 2 was the a, b is the 3, raised to the power of x. We don't plug in for x or y, just like when we did a linear, we didn't plug in for x or y. There's our general form. You could have also written it without the multiplication sign. You could have used parentheses this way. Okay, so what you're going to do now is you're going to move over, skip this page, and I want you to do the same thing that we just did right there. You're going to do this checkpoint. You're going to write a rule for that function. Okay, so go ahead and pause and do that, and then you can come back to see if you did it correctly. All right, so let's see how you did. These are increasing by 1. So far, so good. Are these getting multiplied by a certain number each time? They are. They're getting multiplied by 4. So what value is that? That's b. b is 4. Remember, our general form is y equals a times b to the x, and I've just figured out that b is 4. What is the a value? The a value is whatever is the y-intercept. It's when x is 0, so that's a -1. And you don't forget your multiplication sign. We need it there because, remember, order of operations, exponent will come first, and then we'll multiply by -1. All right, good work. So let's go back now to example 2. Now we're going to graph what this would look like. It says graph the function y equals 3x, identify its domain and range. So we're going to make a table by choosing a few values for x and finding the values of y. The domain is all real numbers. That means I can plug any number in for x. It's allowed to plug anything in there. You can have to the -2 power. That's 1 over 3 squared, right? Which is what we have right there. So this is why we need to do all that exponent work. If I plug in -2 to my equation, y equals 3 to the -2 power, my exponent is -2. What does that become? Y equals 1 over 3 squared, which is 1/9. Okay? Y equals 3 to the -1 power is 1 over 3 to the first, or 1/3. Any number to the power of 0 is 1. 3 to the first power is 3, and 3 squared is 3 times 3, or 9. So this is definitely not linear, it's exponential. Step 2 is to plot the points, and you have to do a little eyeballing here. So -2 and 1/9 is almost touching the line, but it's not quite touching. -1, 1/3, you eyeball a third of the way up. 0, 1's right at its spot. 1, 3, and 2, 9. And this is what exponential curves do. They zoom up. The other thing they do is they never, ever will touch the x-axis. So when I draw this, it just keeps getting closer and closer and closer, but it's never actually going to touch. So one thing that I'm going to be looking for in your graphs is that it looks like mine's touching clearly, right? But it definitely is not going below. I've made it just as close as I could get it, and I didn't draw it below like this. This would be incorrect. Okay, if I can tell that your line's going below, that's a mistake. So make sure that you're very careful that it doesn't go below. Okay, now we want to talk about what is the range. So we said the domain is all real numbers. Do we have any limits on the range, the y values? What do you notice? If I just told you the y values are never going to touch this x-axis and they're never going to go below, that means y can't be 0 and it can't be any negative numbers. So my range is all positive real numbers. I could have also said my y values are greater than 0. That would have been another way to write the same information. Okay, so go on over to number 2 in the checkpoint. You're going to make your own table, identify the domain and range. You can pause and then see how you did. All right, now you got to be careful when you pick your points. If you just start at 0, you're not going to be able to eyeball what happens in this direction. So you really should be going from -2 to 2. 5 values are really kind of important as well. I'm going all the way in my range from a -16th all the way up to 16th, and they had to count by 2s to get it all to fit on the graph. The last thing I need to do is identify the domain and the range. So the domain, is there any value I can't plug in for x? Nope, it goes in both directions, so it's all real numbers. Every number works. And then the range, are there any values that y cannot be? Yep, it can't be those negatives, and it can't be 0 again. So we'd say all positive real numbers. And you're wondering maybe why I'm saying real numbers? Because they're not imaginary numbers, and yes, we actually have imaginary numbers. I think we've talked about that in class a couple times before. We're not to those yet, so we need to use our definition and say all real numbers, all positive real numbers. All right, you're doing great. Back to example 3. Example 3 now, we're going to graph. Notice that our value of a isn't 1 anymore. It was in the previous 2 problems. And then we have to compare it with the graph above. So here's y equals 3x. That was this graph above. Now they've stuck a 2 in here, and we need to do order of operations when we solve this problem. So the first thing they want us to do is we're just going to fill in our table so we can see what happens with the y values. So we're using the same values from our y up here. So 1/9, 1/3, 1, 3, and 9. Well, now what are you doing then? You're doing the same y equals 3x, and then you're just doubling it. You're multiplying it by 2. So that's kind of helpful that we had that last table, because now we just multiply each one by 2. So 2/9, 2/3, 2, 6, and 18. And now what I'm going to do is I'm actually going to graph both of them, because I want you to be able to see the difference. So I'm going to put this first one here in orange. Go ahead and do that right now. -2 1/9. Careful on the numbering, it goes by 2s. On the y-axis anyway. Okay. So it's going to do this. And it's going to shoot right up. Okay. In purple, I'll do the one that was multiplied by 2. Down here, it's going to basically look like it's the same point. There's no way to really distinguish between those two. I can get a little higher there. Now at 0, 2, you can definitely tell that they're starting to separate. 3, 6. So 9, 18. All right, so my orange curve, I need to make it go down just a little bit more. Because 2, 9, I did not put in the right spot. There's 2, 9. I got to fix my orange curve. I did 3, 9. There's my orange curve. Just ignore it. I ended up doing my orange curve where the purple guy goes. So here we go. Okay. All right. So I don't like how my curves look. They're not doing a very nice job. So here's what we're going to do. We're going to look at these right here. Okay. So this y equals 3x. What color did I make that guy? Orange. Here's y equals 3x. Right here. That's the second one right here. Okay? And then this one right here. That one right there. It's hard with my markers. It's a pretty thick line, so now my orange looks like it dips down below. So you got to just be careful about that. So there's my purple one. Okay, so what's happening here is that the y values are 2 times the values of the original. It was multiplied by 2. So this is called a vertical stretch. What I've actually done is I've stretched it vertically. Vertical is up and down, and I've stretched it this way. If my graph had looked like this, that would be called a vertical shrink. Like somebody sat on the orange line and made it wider. This one, someone's taking the orange line like it's a rubber band and it's stretching it up, and they're really close to each other right now on this graph, so it's hard to see that. But it's definitely steeper. When it's steeper, it's a stretch, and when it's not as steep, it's called a shrink. All right, so let's go over to this guy. What would happen if I multiply it by -2? So what you're going to do is you're going to take that same table, and I'm going to write y equals 3 to the x, and then y equals -2 times 3 to the x, and I'm going to take those same x values and those same original y values that we did in the first problem there, and now I'm going to multiply each one of those by -2. So now I have a -2 ninths, a -2 thirds, -2, -6, -18. Whoa, what is that going to do? So I'm going to graph this guy. I'll just graph him in green. And you're going to see what's going to start happening here. So -2, -2 ninths, -1, -2 thirds, 0, -2, 1, -6, and 2, -18. And you just try your best to do a nice smooth curve when you're drawing these, okay? So this guy goes down. Remember, our original guy was an orange, did something like this. Oops. Okay, that was our original guy. All right. So, first of all, what ended up happening? Is this one steeper or not as steep? It's actually steeper, so this is a vertical stretch. The other way you can tell is you look at that value of A, and if its absolute value is greater than 1, you know you're going to have a stretch. If the absolute value of A is less than 1, it's going to be a shrink. So if the graph, it's hard to tell if it's a shrink or a stretch, you're going to use that rule, just the same way we did for steep and not steep with linear. So this is a vertical stretch, and it's also flipped over the x-axis, so that's called a reflection. All right? So a nice written out answer of that, if I wanted to take the time to do it, which you will do on a nice assessment, you would say the graph of y equals -2 times 3 to the x is a vertical stretch and a reflection in the x-axis, that means I flipped it over the x-axis, of the original graph, y equals 3x. Okay? All right. I know it's long notes. We have one more page. So here's some general notes that we need to kind of like get everything in our mind, because now we're making the leap to the next step, which is the real world problems. So in these, A is the y-intercept, and what does that stand for linear for y-intercept? It's the initial amount. So A in exponential is the initial amount, starting amount. R is the growth rate. So see, we've done something different now. It's not a B. R stands for rate, and it's the rate of growth because this is a growth model. So it's the growth rate. 1 plus R, so if you say the whole thing together, that's called the growth factor, because they may give us different pieces of these puzzles, of the puzzle here for these problems. T, what does T usually stand for? The time period. All right, so let's look at example 4. They're going to give us some of that information, and we're going to put it into the exponential growth model that we saw above. All right, so it says investment. You put $250 in a savings account that earns 4% annual interest compounded yearly. So there's your clue that we want to use the growth model. We're growing over time. You do not make any deposits or withdrawals. How much will your investment be worth in 10 years? So basically, if you took $250, they were going to give you 4% annual interest, which is actually a really good percentage, way higher than we normally have in real life. And you just let it sit there for 10 years. What would that $250 be worth? So to figure this out, we have to figure out the different pieces to the puzzle that they gave us. The initial amount is $250. All right, so the initial amount is $250. The interest rate is 4%, but you know we can't put a percent into a problem, so how do we change that to a decimal? Be careful, it's not 0.4, it's 0.04. And the time period is 10 years. Okay, so here is our model. Let's plug in what we know. So we know y equals A. A is initial amount, so that's 250, times the quantity of 1 plus the rate, which is 0.04, raised to the power, which is the time, which is 10. So to kind of make notes of what we just did, we've substituted 250 for A, we plugged in 0.04 for R, and 10 for T, and then we have to simplify. So you do order of operations, parentheses are first, 1 plus 1.04 is 1.04, 1 plus 0.04 is 1.04, okay? And then we can plug this in our calculator. We do the power of 10, and then multiply by 250, and what does your calculator say? It's going to be rounded. It was approximately $370.06, because we want to round to the nearest penny. This is money, right? So the hundredths. So you'll have $370.06 if you just let it sit there for 10 years. I don't know if that would be worth it or not. Okay, so last one finally. Hooray! Number 4 here. In example 4, let's say they change it to 5%. What would the overall money end up being in the end? So pause the video, go ahead and work it out, and then come back and see how you did. Okay, how'd you do? Notice that when I was calculating here, I did the power of 10 first, then I multiplied by 250, and because I had a long decimal, I rounded to the nearest hundredth because we're dealing with money. So I have an approximately sign, and then my answer says you would have about $407.22. All right, continue on to the next step. See Mrs. Wyman if you have any questions.